and the glass falls down before structural damage occurs. So that's a different set of assessment, and we have to look at envelope. And envelope includes doors and windows. And then you have to control debris, like in this North African Embassy project, they were considering putting fences to capture debris flying into the building. So they eventually decided that maybe they can do without it, and they claimed that they saved $3 million. Imagine they were going to cover the entire building with wire mesh, right? So I said it's not necessary so long as you glaze it. So flying debris control is another thing. Levels of protection are related to performance levels that we will talk about this afternoon when we discuss seismic. In seismic earthquake engineering, we talk about how do buildings perform. In blast engineering, we talk about how much you protect it. It's the same thing. If you have very low protection, which means the building is important but not that important, then you design buildings for collapse prevention. Collapse prevention means your building, you sacrifice it so long as you save occupants. Building comes on the verge of collapse, but it doesn't collapse. That means your deformation limits, your ductility has to be designed accordingly. If you have low level of protection, it's better than very low, and you design it for life safety, and the life safety limit for ductility is more stringent. Medium is immediate occupancy. You let people leave, you inspect the building, you can call them back into the building. And then high level of protection is command and control center. During and after the attack, you don't need to leave the building, it's operational. So building remains elastic. So there's explosion outside, people are scared, but they don't need to leave because you design it such that it remains elastic. Of course, these concepts are vague concepts until we look at force displacement relationships. Again, structural engineers look at numbers. Force displacement relationship, these quantities B1 through B4 are known as response limits. If I have high level of protection, and I just said that my structure has to remain elastic, so I design it for B1 ductility level, and B2 is medium level, which is used for life safety, and then you have low and very life is collapse. It's on the verge of collapsing, but you allow the building to displace this much. So once again, given level of protection that the owner is willing to pay, then as a structural engineer, you design it such that displacement, nonlinear displacements are attained within that category. Okay? So we do in the design procedure single degree of freedom analysis to calculate response demands. When you do single degree of freedom analysis, if you do nonlinear analysis, there are similar charts for nonlinear analysis. It tells you how much moment is imposed on the element, how much displacement is imposed. So you have to design in detail for those two demands. And similarly for non-structural elements, I'll talk about window design and wall design. And then we correlate this demand with capacity. If capacity is higher than demand, then we're in business. Otherwise, we have to go back and increase capacity. So response limits are given in the standard. So if I want to design for immediate occupancy, what is the deformation limit that I designed for? Right? We'll talk about support rotations. We'll talk about ductility ratios. They are specified in tables in the standard. But then standard specifies them in different categories. Primary structural members, which are responsible for strength and stability of the building. Secondary structural elements which are like beams. If they fail, only that local area is damaged. It's not like first-story column. They're still structural, but of secondary importance. Non-structural elements are essentially infill walls, windows, doors. They have a different category here. So I have to look at them one by one. I don't want to get too fancy about nonlinear analysis, but you can have plastic hinges. If you have column fixity top and bottom, of course, when there's blast effect, there will be moments taking place. Moments will be highest at the end, so these hinges will form, and then third hinge forms when there's collapse mechanism forms. You can do sectional analysis, moment curvature analysis, assume hinging length, you get moment rotation, and area under moment rotation gives you moment displacement. That's how you find your inelastic displacement. And that displacement is compared with what's given in the standard as response limits. And here's another example of a simple supported element. Basically, it's the same, but you do single degree of freedom analysis and get displacements and forces for design. These are response limits, and I'm only showing you, I'm going to show you two tables, but there are other tables for steel, timber, masonry. These are for reinforced concrete. Response limits are specified either in the form of ductility ratio, which is mu, or in blast engineering, funny enough, they deal with support rotations. In structural engineering, we like to deal with ductilities. In earthquake engineering, we talk about ductility because that's a measure of inelastic deformation. But in blast, because they look at glass windows, they look at doors, they're not security. The whole profession evolved from security people, not from structural engineering people, and that's why they started using support rotations. Support rotations are used under high displacements, so it's either ductility or support rotation that is specified in the CSA standard. So if I'm going to design a building for very low level of protection, that means I'm interested in B4, so my column has to have support rotation of 10 degrees. If it exceeds 10 degrees, then it will have to be strengthened. And similarly, the other one was for beams and slabs. This is for flexion axial load, 2 degrees for vertical elements, columns, and walls. And these are the ductility ratios. Ductility of 1 means your member has to remain elastic because response quantity B1 is associated with operational performance level for which you need very high protection. Okay, so once you have different levels of protection and you then find the damage levels, you correlate that with demands, as I will explain it to you. But these are different levels of damage. So response quantity greater than B4, like support reaction, support rotation in the case of a column greater than 2 degrees, means blowout. That means column will fail. Okay? So if you don't want blowout, it has to be less than that. And hazardous failure, heavy damage, I'll talk about describing those levels. Now, here's an example of column failing under blowout. This is our last simulator, shock tube, that we have at the University of Ottawa, and I'll show you a lot of applications after the coffee break. But this is blowout. You can see even the longitudinal bars rupture. This is 1/3 scale of one of the autonomously columns that we modeled, and it completely failed. Now, hazardous failure is not as bad, but it is still bad enough that you may not be able to use building, because as you can see, there's a permanent deformation. Concrete spalled off and steel has yielded. This is quite high, and it is not acceptable if it's in main elements. Now, moderate to heavy is acceptable depending on how much repair you want to use And this has a little bit of permanent deformation.